Here have some extra region that are not covered.
Okay, and once you have assembled this data, let's plot it. Depending on what you're familiar with, you can use XMGrace or gnuplot or whatever. So if you're using XMGrace, you type XMGrace, then you go to data, import, ASCII.
Well, in principle, the initial configuration should the initial configuration which is closer to the final configuration should be very fast. Because we start from closing point. And sometimes some similar problem the atomic will function
Okay. So now run a set of decide which value you think is converged enough. I mean, that depends on you and what purpose you're going to use the total energy for. I decided that 20 Rydbergs was good enough, but you can choose whatever value you want. Fix the E cut WST as that, and now instead loop over the cable. So you can either modify the existing shell script to do that, or you can do it by hand. Okay.
I need this
You make a really big thing. I guess we'll have a look at it and see what we can do. 4K points and blah 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 blah.
Do you have to talk to that girl?
Yeah, so now you can this shell script into another one called assign points and then edit that so that instead of putting with
relax control state. And then Y six. Y. Oh no, you just wrote from this shell script. I was always the highest user. Yeah. We didn't have access to any computer, so it's just like creating a religious page. Probably should have changed the name. We're gonna have two tabs on here. I thought that was what I thought it would be.
Okay, so this is the graph I get for the total energy versus Nk. So you can see that as I increase the number of K points I have, it starts converging to some value. In this particular case, it happens that the convergence is monotonic, but it need not be so. And then I've asked this question, why did we use Nk1, Nk2, and Nk3 the same value? Why did we always use 2 to 2, 4 4 4, 6 6 6, etc.? Huh? Yeah, because it's cubic, and so your three primitive vectors are equal length in real space and physics. Okay. So now we'll do the next step, where we'll fix P cut WFC and NK1, NK2, NK3 to whatever value is wants. And now loop over the lattice constant.
What's the mixing beta mean?
It's how much of the new wave function you put into the old wave function. So for example, it's roughly like you have 70% of the new intensity and 30% of the old one.
Okay, it's a coefficient for new density. Okay. Yeah. Okay, thank you.
to the sample. Well, I got emails from
Can run till quarter to 5, so quarter to get there.
I'm supposed to move over the lines. And after that, do you have the HTML file with us or step by step?
Nine free days. 9 free days. I didn't think the energy would go down.
Get that instruction. You see the instructions that told you what value. Usually was minus and x order, that wasn't working. I think it wasn't working, so you have to say the input format. Yeah.
I was like 10 points.
Does anyone need help? Okay, everyone, whatever stage you're at, just stop now and let's look at the screen for a bit, and then we'll move on to the next exercise. That's because we have a talk at 5. So, okay, so I'm going to plot the data with X and Grace. Yeah. Okay, so here are the data points. So you can see that your energy versus lattice constant is going to have a minimum somewhere here. We're going to fit that in a moment. Is this curve symmetric or is it not about the minimum?
No.
And do you expect it to be? So if the interatomic interactions are not harmonic, which is in general true, then you expect it to be somewhat asymmetric. That is, it's harder to squeeze the crystal than to expand it. And now to get some idea what the equilibrium structure is, etc., we type here ev.x. So it asks for the type of Bravais lattice, and in this case it's FCC, so I type that. Now there are different formulae that people have developed for how the energy varies as a function of lattice constant, and it's named after the people who developed them. I'm going to choose 2, which is a Birch equation of state. This is the file that contains my input data, and I'm going to put it in one that's called fit.out. Okay? So here is the result of the fitting procedure. So A0 is the equilibrium lattice constant. In this case, it's found to be 10.348. Okay? K0 is the bulk modulus, and it's found to be 870 kilobar, which is less than the experimental one. The next one is the pressure derivative of the bulk modulus, which gives you some information about how anharmonic your interactions are. And here you can see that one column is the value that you supplied, and the other is the fitted value, and in this case, up to 5 decimal places, the fit is exact. So the difference is 0. Okay. So there were 2 more exercises in this one, but we're going to skip it for lack of time. You could come back later and try it, and we'll move on to the. Actually, I think we're moving on to exercise 3 now, right? Brandon, you're going to do 3? Okay. Close up everything. You want to log in as yourself?
Get my keys exchanged out.
Are you going to be back?
Yeah.
I have no idea. I'm just copying Look like the value.
Okay, so if you want to load up the instructions for the exercise 3. We're going to do bits and pieces of this, but not the whole thing in the interest of time. There's a bullet sheet higher. All right, so the main thing about this exercise is we're going to look at the degauss parameter, which is the width of the smearing that Shobhana talked about today, and how that affects the energy. So there's a sample input, al.sample.in, and if you take a look at that, under the system name list, we've added a line for occupations equals smearing, so we're turning the smearing parameter on in the electronic occupations. And then we specified Marzari-Vanderbilt smearing, and we have a degauss parameter, which is the width of that smearing in units of Rydbergs. So this is aluminum, so it's an FCC crystal. It has only one atom in the primitive basis. So we can look at just quickly look at the crystal. I don't want to spend too much time doing this, but spend just a minute to convince yourself that that's standard FCC crystal. So 12 atom coordination, like you'd expect for an FCC. And the first thing we want to do is just run the self-consistent calculation that's in that sample file. Just like we did before, the instructions are in the HTML file on how to do that. And it should be a really quick calculation. All right. So now if you view that file, you're going to see a few differences from what you saw in the silicon. And that has to do with the fact that we're looking at a metal now. So in particular, there's only 3 valence electrons in the system, but we've calculated 6 bands. So why do we need more bands? Because we have the smearing parameter, so we need to smear across unoccupied states as well as occupied states. So we have 6 bands that we're calculating with only 3 electrons. And because we've used these smearing occupations, actually get out of the bottom here, the system, if you go down to the very bottom of the file, after it finishes the calculation, it outputs for each K point the bands, and then in addition it tells you the occupations of each of those bands. Then at the bottom of that, scroll down to the bottom of the K points, it also outputs the Fermi energy. Okay? So you can see how that compares to the levels of the bands, the occupancy of the bands. So for instance, at this particular K point, the first 2 bands should be occupied, the third one is unoccupied, which, sure enough, is the case. Okay, so that was just the sample. There's also a script inside that same directory. So if you you take a look at that script, al.sample.sh, there's a loop in there that's designed to run across both the k points and different values of the dGauss parameter. Okay? So I don't know how familiar people are with shell scripting, but I'm just going to assume that you sort of know how to follow these things. So in particular, we've chosen 5 different values of dGauss, which again is the width of that smearing parameter in Rydberg's, from something that's reasonably small to something that is probably higher than what you'd want to use for most applications. And then for each of those values of the dGauss parameter, we're iterating over 4 different k-point samplings. And that'll be 666, 888, 12, 12, 12, and 16, 16, 16. So the script does a self-consistent calculation for each of those sets of parameters and outputs a file that has coded in the name the dGauss parameter and the number of k-points. So take a moment and make sure that you can follow what's going on in the file. And then when you're ready, go ahead and run the script. It'll take maybe a couple of minutes to finish. Again, because it's a cubic system, the number of k-points is the same in the x, y, and z directions. Okay, mine's done now, but I'll wait a few minutes for people to catch up. Whose script is finished? What? Everyone else is still running? Yes? Okay, who's still running? No one's doing either one? You're still running?
Cool. So, wrap it.
Most people done. The script should be finished. Finished? Okay. Move on. All right, so if you grep exclamation point, you should be able to see all the energies for all of the different calculations. So what we want to do is organize these into some sort of plottable form. And in particular, we're going to organize them by the dGauss value. So we'll have a file for dGauss of 0.02, one for 0.04, one for 6, one for 8, and one for 10. That has the number of K points and two columns. The first will be the number of K points, and the second will be the energy. So you can do that using whatever fancy tool you like, a combination of grep and gawk, or do it by hand if you want to. Just copy the what's on the screen. So just like the instructions say, I'm going to put that in a file that is called that. Sorry, the border's screwy. Some of you probably have much faster ways of doing this, but once you have all those files, then go ahead and plot them. And for some reason that we haven't been able to figure out, XMGrace doesn't seem to like to take arguments from the command line. So you may have to just load it and then input the file data manually. Oh yeah, yeah, sure. Yeah. I'll just plot these up and then look at it.
Say when you are done.
All right, so here I plotted all 5 of those data sets. And so what we want to do is figure out where and when the energy is converged to get a proper value of both the d-Gauss and the number of k-points. So if you look first of all at the number of k-points, all 5 of these curves are fairly flat by about 12. So I'm going to go ahead and say that 12 is probably good enough. In terms of which d-Gauss value to use, by the way, the black curve is 0.02, then the red curve is 0.04, this is 0.06, 0.08, and 0.10. You see 0.10 is probably too high. So the energy that we're getting looks quite a bit different from what we're seeing in the other cases. This is the most accurate point that we have. So this is very small d-Gauss and very high number of k-points. So we want to get as close as possible to there without dealing with the computational expense of lots and lots of k-points and low d-Gauss. So we say 12 k-points and probably maybe the green curve, which would be 0.06, is probably sufficient. All right. So did you want to say something? Yeah.
So I know that some of you had a technical problem due to the randomness of this, the configuration of these machines. So if some of you has the following problem, that opening a new shell does not find, could not run pw.x on the command line, is there anyone that has this problem? You? So, okay. If you try to open another terminal, and you see that you cannot see the variables, you cannot run pw by typing pw.x. Can you try, everyone, a moment, just, you go on the... You go like here, you do open tab, for instance, or terminal, default, and in principle you should see pw.x again. So, does it work for everyone apart from him? And
Doesn't work.
doesn't work? For who doesn't work this? 1, 2, raise your hand, please. Okay. Those of you who have this problem, here